Okay. Um, so in the digital electronics, have you gone through the combinational logic circuit? We already completed till combinational logic circuits, right? So have you revised all the topics once again? Sir, decoders, encoder. Hello. If you don't want to answer, I can stop the session here. Whenever you are able to answer, then only I can continue. Whenever. Hello. For the session. I will intimate same thing for the group also. Those,
I just completed. The others are I'm going to.
okay. What about Lahari? Okay. So today shall we discuss with the digital electronics or Verilog HDL? Okay. Digital electronics. Okay, fine. And designed demultiplexer decoders also. And in full orders also we need to discuss some like how to implement logically different types of using operators, using conditional operator, concatenation operator. We need to write the program. So I think everyone gone through the operators. In today's session we will discuss overview of all combinational and then operators. Okay, so in the next session we will continue with the how to design the always block, initial block, and forever for each loop. The clock, how to use we already discussed, but loops we need to discuss more into the loops and the designs of combinational. And next session will be on blocking assignments, non-blocking assignments, begin and blocks, fork join blocks. These are very important in Verilog HDL to follow all the rules. Okay, so once blocking, non-blocking, fork join, parallel execution blocks are completed, then we'll start with the sequential logic circuits. Okay, so next week schedule is Monday is for designing of combinational logic circuits. Okay, Wednesday is also somewhat we will discuss a few combinational logic circuit one end of session. and half session will be blocking and non-blocking assignments, the loops and all. Okay, and Friday session will be into sequential logic circuits. Okay, so again next week I'm just telling the schedule for you as of now, so that you will be prepared for the coming sessions, right? So what we need to go through the before joining the session. So that's why. Okay, so in today's session, have you gone through the difference between ripple carry adder and carry look ahead adder? So coming to the half adder.
Yes.
Half adder means it have a two number of inputs, A and B, and two outputs, sum and carry. Because of two inputs, we'll have the four combinations 00, 01, 10, 11, and some carry 00, 10 according to the addition operation. Okay, diagram. From the expressions, we need to draw the circuit diagram. Okay, so for full adder, so if you want to do the addition for multiple number of bits, not only single bits, for multiple number of bits, 3 bits, we can go with the ripple carry adder or carry look ahead adder. Okay, so this is what the full adder, it have 3 number of inputs and 2 number of outputs. But in this also we have lot of mostly where the applications are, where do we use in arithmetic logical operations, ALUs, and like how we design the multiplexers by using the full adder. These type of things we need to discuss. I already shared you the assignment 1. Have you gone through the second assignment, combinational logic circuit? Is it completed?
Some of them I have done.
Okay, okay. So BCD to 7 segment display, and how to design the demultiplexer using a decoder. What is the parallel application? Have you gone through those? And how to do the n-bit parallel addition. So full adder, in the sense we can do easily by using let's just 0, 0, 1 output is 1. But if there are multiple number of bits, like 1, 0, 1, 0, 1, 0, so these input these are n-bit, like a flip-flop will store a 1 bit for a multiple number of bits. To store multiple number of bit n-bit, we use the shift registers. Okay, shift registers are nothing but connecting in a hierarchical way. Okay, in the same way, for ripple carry adder, we connect n number of full adders. We already seen the Verilog program also for ripple carry adder in structural modeling. Okay, so in the same way, the carry will be propagated from one to other. Okay, so like just taking the multiple number of like copies of full adder in the ripple carry adder. But at the same time, we can also do the addition and subtraction operation. Okay, so how we can do the parallel addition and parallel subtraction here? If you observe the parallel subtractor here, so how it is working? How it is working?
We have to tell, ma'am?
Yes.
Yeah. Just sequential, ma'am. After carry from the first 2 bits A0 or X0, whenever C0 is 1, it's like A0 plus X0 is the complement of, due to C0, X0 going to be complement, and A minus B will be performed, and S0 and C1 will be generated. And using C1, C1 is 0, X1 is available, A plus B operation will happen. If C1 equal to 1, A1 minus X1 will happen. Like that, after some delay of the carry, first C1 will get, next S1 next second delay of the F full adder C2 will get, third delay of the full adder A2 C3 will get, and total delay is Tn equal to n minus 1 of carry plus maximum of any sum or carry of final stage.
Okay, so parallelly, how it is doing both addition operation and subtraction operation?
Depending on the carry. If carry is carry is 0, it will perform addition. Carry equal to 1, perform
Carry equal
difference.
to 0, it do the subtraction operation. So how it is doing the subtraction here?
Not addition. Carry equal to 0 means subtraction. Like 2's complement.
Okay. So how the 2's complement is happening here? Any other answers from others?
Hi ma'am, it is performing subtraction as a plus of minus b. That minus b is the 2's complement of b. So it is basically adding the 2's complement of b to a. So we are performing the subtraction of a minus b.
Okay.
With carry equal to 0, it's a 1's complement addition, ma'am. Like
Carry plus
a plus
1. Okay.
Carry equal to 0, it's 1 complement addition. Carry equal to 1 means 2 complement addition. A plus 2's complement of B addition.
Okay. Okay, fine. So 2's complement of B is nothing but it's doing subtraction parallelly. So if you see here, just A equal to, here C equal to 1 mode. We can call it as a mode. For addition directly, we can do the add operation. But if you take as a subtraction, suppose if you see here, add bar sub. That means C equal to 0. Add bar is nothing but equal to 0. Sub is not complemented. Not complemented means equal to 1. So equal to 1 means it's a subtraction operation. Equal to 0 means it's a addition operation. Okay. So if one input XOR for XOR operation, if one input is 0, next input will be buffer. Buffer means same value will be getting here. Maybe it's 1 means 1 will be getting here. With this 1 here with this 0, both will be added and getting the value. Okay. Suppose this B0 is 1. B0 means 1 means if any one of the input is 1 for XOR gate, it work like a complement, right? So complement value will be generated here. With that complement value, if I do the addition of these two, then it will be the subtracted value, right? Understood, everyone? Hello.
Ma'am, could you please repeat?
Okay. So where we are giving this signal is applying here 0. Okay. Normally A equal to 1, B equal to 1 is there. So A equal to 1, B equal to 1, C equal to 0 we need to add. Okay. So here 0, one of the input is given to 0. Then what is the output? Nothing but buffer. So here whatever the 1 is there, here we get the 1. Okay. So 1 plus 1 is nothing but 1 0. That 1 will be going to the next propagation to the next, and 0 is getting to the here. Okay. And again next, if you are doing subtraction, Here C equal to 1. So that means this value will be 1. Okay. So if any one of the input is 1, then what is the output? Whatever the 1 is there here, output will be 0. Okay. So this 0 plus 1 will be 1. That is nothing but subtraction, right? Okay, so this is how we can do the parallel addition and parallel subtraction. But how we are going to write using a program, Verilog HDL, that is important. How we can implement a parallel subtractor or adder using the Verilog program. Already, if you observe, we have written for ripple carry adder. Okay, ripple carry adder means what? Like one full adder, second full adder, third full adder, fourth full adder. Okay, so for first, I will share you the codes also for everyone. I will share you the codes, so you can copy and you can use. Okay, so here A, B are the inputs. Here also A, B are the inputs. Here A, B. Here also A, B are the inputs for normal ripple carry adder. So C is one of the input, and here C is propagating, and here also C is propagating. Here also C propagating. Output will be S0, S1, S2, S3, and here last carry. Okay, so this is normal ripple carry adder. First we will implement the full adder and we will take the n number of copies in the structural modeling. Okay, so for same here just we are connecting this C value to this. Here we are implementing one XOR gate. One XOR gate. For these we are putting the C as a mode, either add or sub. Next, this will be the B, actual B, and this will be the A. So B, A, and one of the input of XOR will be connected permanently to either 0 or 1. Based on 0 or 1, it will be calculated addition or subtraction based on the mode signal. Okay. So in that program, in the Verilog program, what you need to do? We just need to add the XOR block. Okay. Whatever the output of XOR block is there, suppose you are considering this output as a wire connection. Okay, so this output of XOR is connecting to the input to the full adder, so it's a wire connection. Suppose this wire connection will be W1, and here this wire connection will be W2, and here wire connection will be W3. Like that you are considering the wire connections. Main output input ports will be A0, B0, B1, like that. Another port is C0. C0 is permanently connected to one XOR gate. Okay, so if you go with the Verilog program, everyone try that. In the last session, I told you to try with the always block. How many of you did that one? I got responses only few members. Have you tried with the always block? So here one full adder we have connected. In the same way, A, B are there. Okay, A, B are the main inputs, but B input is connecting to the XOR. So you need to write another module. I'm just showing, but you need to do. Okay, XOR in. Okay, so what will be the outputs and inputs for XOR? So A, B are the inputs. C is the output for XOR. Input A, comma B, output C, assign. Suppose you can use assign, or you can just generate a XOR by using the gate level modeling. How you will generate just XOR X1 A comma B comma C. Okay, end module. Or you can also use the assign, anyone only. Assign C equal to A XOR B. Okay, any one enough. So this XOR in, whatever the XOR in is there, you need to take the copies here. XOR in, XOR 1, XOR 2, XOR 3 and XOR 4, and give the inputs and outputs. A will be the input, A0, B0. A will be the input, and B also input, and C also the one of the input, 3-port input. Okay. Oh, okay. Sorry. Only BC will be the input. For full adder, A, B, C. 3 we need to consider, but here B, C will be the inputs. Okay. So C will be connected permanently to either 0 or 1. Okay. C will be common for all. Okay. And B will be changing. So first XOR gate, B value will be B0, and then B1, and then B2, B3. Like that it is changing. C will be common to all XOR. Okay. So what is the output here? Output will be any wire signal. Consider as a wire. Suppose wire W1, W2, W3. Okay. So here output will be wire W1 initially. Here I took first inputs, then output. So that's why you need to put first inputs, then output here. Or else if you mention first output, then inputs, then according to the port. Okay, however we consider in the same way, we need to mention here. Okay, according to the port. Same. Okay, connect all the connections here and check the output. Okay, write a simple test bench, give the mode signal here. Input first 50 time units or first 200 time units for addition operation, next 200 time units for subtraction operation in test bench. Okay, so do this and submit by Monday. Clear? Everyone understood how to design parallel adder or subtractor using Verilog HDL? Hello.
Yes, yes.
Yes, ma'am.
Any other ideas from your side? Any implementation ideas? Mostly these type of circuits we can design in the same way. If you want to go with the behavioral modeling, we can use, but it's somewhat complex. Okay. If you want to check in a structure, if you do the synthesis, same structure we will get XOR gate and connecting in a block level, same. Okay. So mostly we don't write the behavioral modeling, and data flow modeling will be the complex. So this would be the best. Okay. And for logic design, multiplexer. What are the applications of multiplexer? And how do we design different gates using a multiplexer. Have you worked on that?
Yes, ma'am.
Yeah. So can you tell me?
Like basic gates we can implement using the mux system, like 2 is
Basic.
to 1 mux.
Okay, suppose I want to design a XOR gate by using a 2 by 1 multiplexer. Okay, so how I can design a XOR gate using 2 by 1 multiplexer? One output, two number of inputs, and one selection line.
Like I use two multiplexers, ma'am.
Two
One is for
multiplexer.
complement. One is for complement. First, I will give A as a select line for first 2 is to 1 marks, and 0 1. Like for 0, I will give 1. 1 I will give 0. I will get a complement. Then I will use that A complement as a 1 for one I1 input for the second 2 is to mark 1 marks, and B as a select line, and A will give as a 0. Then I will get A bar B plus A B bar. Two multiplexers we can implement XOR gate.
Okay, okay. Any other ideas from others? How can we implement a XOR gate using 2 by 1 multiplexer? Suppose XOR gate means 0 0 0 1 1 0 1 1. Okay, so output will be 0
A bar B
1
plus A B bar.
1 0. A bar B plus A B bar. Okay. Hmm. Not only like this, we can draw in other simple way also. Suppose I'm considering A or B, any one signal as a selection line. Okay, suppose I'm considering A as a selection line. So here A will be the selection line and B will be the input and this one will be the output. If A is the selection line, if A is a 0, then what is the output? Output is nothing but B. So here B will be connected. So whenever A is equal to 0, output will get B. Whenever A is equal to 1, what is the output here? B bar. So I'm connecting B bar here. So whenever A is equal to 1, this B bar value will be assigned to the output side. So this is how we can design 2 by 1 multiplexer for XOR gate. Everyone understood?
Yes, ma'am.
Suppose I'm considering as a NAND gate. So how can I implement a NAND gate using 2 by 1 multiplexer? NAND gate using 2 by 1.
So NAND gate, if A equal to 0, the output will be the B bar. I mean, complementary, whatever B is there, the output will be the B bar. And if A equal to 1, output will be the A bar.
Okay. So 0 0 for 0 0 output will be the 1, and here also 1 1 0 for NAND. So if A is 0, then what will be the output? Output will be 1. So permanently this will be connected to the 1. So output will be getting 1. So if A equal to 1, that means A is the selection line here. If A equal to 1, output will be B bar. Okay. So this line will be connected to B bar out. Okay. Like that, how we can implement the XOR gate using a 4 by 1 multiplexer, not 2 by 1, 4 by 1.
Way we can give select AB as a select lines, and we will give 0 1 2 3 as a like 0 1. Directly we give the truth table output as a input. 0
XOR gate output. Okay. Selection line is a B now.
Yes, ma'am.
Selection line is AB. Okay. 4 number of inputs. Selection line is AB. So AB 0 0 means this 0th line will be